Let's look at a few things to consider when thinking about incidence and dealing with incidence. First of all, we should have the same consideration as for prevalence. So have a look at those again if you've forgotten them, but basically everything that applies for prevalence applies here for incidence. Loss of participants and attrition bias. We did discuss that a bit with prevalence, but let's look at something here again. So losing track of participants in a study is common and may severely bias results if those who are lost are different from those who are kept. And that's often referred to as attrition bias. So here at baseline, we started with 4 individuals. We started collecting data, but after 5 years, we couldn't contact this person. After 10 years, these 2 people were gone, and so on. If you had a study which included 100 individuals and 30 individuals were lost, and then you had 10 events among the 70 left in the study, then you might have estimated a risk among retained participants as 14.3%. Now, if all 30 lost individuals had an event, then the true risk would be 40%. And if none of the 30 lost individuals had an event, then the true risk would be 10. So the range is quite wide there. But we don't really know anything about these individuals that were lost. Or do we? Maybe we do in our study. Are they systematically different than those retained? Is there something that can predict them not participating? And if so, we have issues with attrition bias, and we have issues with bias in general, that our results are not accurately, or our study is not accurately measuring what we're trying to get to. Dealing with missing data is very complex, and usually some form of imputation of the data is recommended. That is, we try to find some substitute for these to make decisions of what we believe these could be. I'd warn against using worst case scenario imputing, sort of saying that, well, they all died. That's going to bias your results quite strongly. That's a very strong assumption. I'd also warn against carrying forward the latest observation. So for instance, in a study, if you have included, so in this case, it would basically say that you assumed everybody is alive because they were alive at baseline. What I was going to say was that in a study of, for instance, smoking cessation, if everybody at baseline are smokers and the idea is to make them non-smokers, then just assuming that they still smoke is also not a great idea. Those methods may be informative to get some kind of worst case, best case idea, but if you're really trying to estimate the incidence, then using something like multiple imputation with chained equations are usually more appropriate, those type of methods. You could read a little bit about attrition bias on the catalog of bias, and if you're up to it, there's a paper here on multiple imputation using chained equations. It's accessible, but it does require some thought. As with bias in general, we could have a whole course on attrition bias only and the different methods we could apply. I think it's just important to be aware of it at this stage, and when you design studies and when you analyze studies, look at different ways in dealing with attrition bias, because in almost all studies it does creep in. Another consideration when dealing or when measuring incidence is competing risks. So if you're studying occurrence of obesity, then death from heart failure competes with the event of obesity. Once a participant has died, they cannot become obese. Now, if you're measuring all-cause mortality, then there might not be any competing risks because you're just measuring all causes that could lead to death. But if you're looking at the risk of mortality due to a specific exposure, then other exposures that also lead to death are going to be competing. So you have these competing risks. That's something to be aware of, and I recommend reading up on that if you're doing those kind of studies. In the demonstration, I mentioned briefly censoring, and we mainly concern ourselves with 3 types of censoring. Interval censoring, that is, if you do measurements each year, for instance, let's say you do it each year, then you don't know what happens in between measurements. So you don't know if there were events in between or not, and if those, you cannot count those events. So here, for instance, we had 4 individuals start at baseline. At 1 year, 2 of them had had an event, so 2 of them had transitioned, and therefore we say the 1 year risk was 50%. But in fact, we didn't measure what happened at 6 months. So in reality, these 2 individuals transitioned, and then they transitioned back before you had a chance to measure them. So again, if you're dealing with death, this is not an issue, but if you're not dealing with death, then it is an issue. Also, it would be an issue with death if you're looking at granularity, because you're saying that the 1 year risk was 50%. But had you measured 6 months earlier, you could say something more fine-grained, as in the 6-month risk was 75%. So that's something to think about, that we cannot, in most cases, measure all the time. So there's going to be blank spots that we don't see in between these intervals. Right censoring is when a subject leaves the study before an event occurs, or the study ends before the event occurs. So some people might survive beyond the study design. Then the data is right censored, and that's really a form of attrition bias. Left censoring is if a subject has already experienced the event before enrolling. That would be, for instance, if you're looking at the incidence of a certain type of cancer, then if they already have that cancer at baseline, that's a type of left censoring. Now, that makes computations of risks incorrect, and hopefully if you have a well-defined screening criteria for who can be involved in a study, you could avoid this. But sometimes it's unavoidable, and this might happen. So left censoring could mess up your measurements in that case. A little quick note on the fact that prevalence is not incidence. It ties in with the interval censoring here, but it's also, from a practical perspective, sometimes we have to think about the two as similar. In this case then, risky drinking was measured after 10 years in a cohort of non-risky drinkers. The prevalence proportion of risky drinking was 50%. Okay, so the prevalence proportion here was 50% because we measured prevalence here after 10 years. It's now then tempting to say that the risk of risky drinking was 50%. But that's not necessarily true, because we haven't then been able to capture individuals that actually transitioned and transitioned back. Now, over a shorter time span, we have to think about prevalence as incidence, and be aware of interval censoring. One way of avoiding this is making sure that you ask participants to recall events since last measurement, so that you actually could capture this, even though there's such a thing as recall bias, which could mess up those measurements as well. But the general idea here is that you can't just think about prevalence as being incidence, because you also need to have captured a cohort that didn't have the factor at baseline. Okay, so there are a couple of things that need to be in place for us to really call it risk, and therefore we can't just set an equal sign between prevalence and risk. Okay, when to use proportion, when to use rate. If the follow-up time is different for different individuals, then the proportion isn't really accurate, as time was different. So recall that when we measure incidence proportion or risk, we care a lot about the calendar time interval. If the calendar time interval is different for different participants in the study, that's an issue, and then proportion might not be the best measurement. In that case, a rate may be better, because then you can calculate the number of person years or person months or person weeks that they contributed to the study. The rate can measure multiple events, proportions cannot. But the rate also assumes this exchangeability. That is, one person followed for 10 years contributes 10 person years. 10 persons followed for 1 year contributes 10 person years. And when we calculate rate, we assume that these years, however calculated, are equivalent or exchangeable with each other. And that might not always be the case. I would say at the end of the day, they answer different questions, and both of them are very valuable. So if possible, you might want to calculate both.